Okay, paper 2 on a page. Right, first thing we have to remember is that energy allows stuff to happen. So energy is what allows work to be done. Energy itself isn't a thing. It is a way that we can use to measure the ability of something to have work done to it. Transfers are what actually do things. So the things we can have in transfers, things like heating or friction or any force, radiation, electrical work, they all actually do stuff. And the only way they can do something is if you move energy from one store into another store. Closed energy systems are one where the amount of energy in the system is equal to the amount of energy out of the system plus waste. So we could take an example of something like a bulb. If that bulb was to take in 100 joules of energy through electrical work, and it released 20 joules as light and 80 joules as heat. Let me just get the words in there. Then this total energy here that is being put out of the light bulb will equal the total energy going into the light bulb. And I will just say as well, I apologize for the handwriting here. It's a new version of the whiteboard. Waste energy is not always heat. So waste energy is whatever isn't useful. And depending on what we're looking at, heat might well be the useful thing. So an infrared heater, for example, it is going to be a good thing that it has that. So in that case, this would be the useful and this would be the unuseful thing coming out of a heater. There are three ways to heat things. Conduction, which is where if you've got atoms together in like a solid, if you give extra thermal energy to the atoms on this side, they will start to vibrate more. And as they vibrate more, they will cause the next atoms to vibrate, causing that vibration to move along the conductor and increasing the thermal energy of the objects as they move through. Radiation, which is the transfer of energy from point A to point B through sound, electromagnetic waves, light is one of those, but it is a simple transfer. And then dissipation is a fancy word for waste energy. Energy getting lost to the surroundings. Work done, always use a distance based on the direction the force is working. So if I've got somebody going up a slope, if it's little Bobby down here who is pushing a box up a slope, and the slope is 20 meters long, but the slope is 10 meters high, which number do we use for working out the amount of energy required to do that? Well, we're going to use the energy that is in the question as acting, we're going to use the distance that is in the question as acting against the force mentioned. So if we're looking at how much work was done against gravity, we would use the 10 meters here. It looks like 16, but I meant 10. We would use 10 meters there. And if we're doing work against friction, we would use 20 meters here. Work done against friction means an increase in temperature. Work done against friction just means that you have made something happen to work against another surface. So if I've got a flat surface here and another flat surface there, if I'm moving one flat surface and the other flat surface is either stationary or moving in the opposite direction or moving in the same direction with less velocity, then friction is going to be caused there because it is work done. There's work done between those two surfaces. Total gravitational potential energy before the fall will equal total kinetic energy after fall just before landing. So if we put the box all the way up here to the top and say that it's got 200 joules of gravitational potential energy, and then the box falls down to the ground, just before it hits the ground, that box will have converted the 200 joules of gravitational potential energy into 200 joules of kinetic energy, assuming 100% efficiency. However, there is actually dissipation in reality. So it will not be exactly 200 joules of kinetic energy. It might be 198 joules of kinetic energy and say 2 joules of thermal energy in the air caused by the box hitting the air particles on the way down. Power is the rate of energy transfer. 1 joule per second equals 1 watt. You have to know about different forces, contact forces like air resistance or drag, friction, tension, and normal force. Normal force is when you have got two objects touching each other, there will be a force at 90 degrees. And if there's two objects touching each other, the forces will always be equal but opposite in direction. Non-contact forces include gravity, magnetism, electrical, and nuclear. Friction is caused by the interlocking of microscopic irregularities. Lubrication separates the surfaces. So if I was to move this surface, if I was to be able to put something in between these two surfaces, that meant that the actual surfaces weren't touching, that they were separated by some kind of a liquid, then I would reduce friction. Okay, now can I move over here? All right, series and parallel circuits. First off, we're going to, well, not first off, but just make sure that you have a look down here. These are some experimental circuit setups that would be quite useful. They include lots of different symbols that might pop up in the exam. Now, I total means total current, and to remember this, we're going to think about the little raisin shouting at you is not a raisin. I am a current. So if I see I, that means current. Total current in a series circuit is equal to I1 is equal to I2. And all that means is if I was to draw a very simple circuit here, with a cell and two bulbs, that the current here, so I here, will equal the amount of current here. I total is equal to I1 is equal to I2. The total voltage is shared. V total is equal to V1 plus V2. So if I have 6 volts in my cell, 2 volts in this bulb, then that means that this bulb must have 4 volts. And the resistance is additive. So if this was a 20 ohm bulb and this was a 5 ohm bulb, then total resistance would be 25 ohms. In parallel circuits, the rules are swapped around. Total current is equal to I1 plus I2. So if I just move that down a little bit so that you can see it, right? If I was to draw a very simple circuit here, again, sorry for the drawing. If the total current up here was 2 amps and the total current here was 0.5 amps, then the current here must be equal to 1.5 amps. The current splits at the junction and then comes back together again at the next one. So it'll split here at junction and it will come back together at junction 2. The total voltage will be same across all of the branches. Now, this is something that people get wrong quite regularly. 6 volts here does not necessarily mean 6 volts into all of the components on that branch. So if I have 2 bulbs, then this entire branch will get 6 volts. If this is a 2-volt bulb, then this will be a 4-volt bulb because the entire branch will get 6 volts. This branch will also get 6 volts. So there'll be one bulb here with 6 volts of brightness. And in a parallel circuit, the total resistance is always smaller than the smallest resistor. In higher tier, you have to be able to remember this. It's the reciprocal of resistance. 1 over R total is equal to 1 over R1 plus 1 over R2, meaning that if we had a 5 ohm bulb here and a 10 ohm bulb here, then total resistance is always going to be smaller than the smallest resistor. It's going to be smaller than 5 ohms. Ammeters are put in series, voltmeters are put in parallel. That's a symbol for an ammeter, that for a voltmeter. You should know these definitions. Current is a number of coulombs per second. 1 electron by itself is useless. Packet of electrons we call a coulomb. The rate of charge flow is what current is. Voltage is the number of joules per coulomb. This is a 6-volt cell. A 6-volt cell will give 6 joules to each coulomb, and that is analogous to 6 volts. Resistance is when the negative electrons collide with the positive ions in the wire. Kinetic energy is transferred to the nuclei. The nuclei then oscillates more, and as it oscillates more, the thermal store increases, so the temperature increases, so the current decreases because there's more electrons colliding with more positive nuclei. Have this off by rote. Know it 100%. Resistance is a very popular thing to put into this exam. In LDRs and resistors, if we increase temperature or light, then resistance breaks down. Generally, if we increase temperature, then we also increase resistance. However, in an LDR, in a thermistor, when we increase temperature, we actually decrease resistance. It breaks the normal rule. LDR, increase light, then you also decrease resistance too. So here's resistance on the y-axis, and then either light or temperature on the x-axis. An ohmic conductor, resistance is constant if the temperature is, which means for every increase in voltage, there is a proportional increase in current. V-axis here, I-axis here. In a lamp, resistance goes up as current goes up due to an increase in voltage. So, as voltage goes up, resistance goes up because current goes up. As current increases, then there's going to be more collisions of the negative electrons with the positive nuclei, causing the positive nuclei to oscillate more, therefore increasing the amount of times it collides with electrons as it flows in. So we see that initially current increases with voltage, but then it begins to slow down. That increase is no longer proportional, and it's because the resistance has increased. In a diode, there is a very low resistance in one direction and very high resistance in the other direction. So we can see here that there's almost no resistance, and so a huge amount of current in this direction, and there is a lot of resistance in the other direction, so it is not able to pass through. My diode is not able, the current is not able to pass through. 1 watt is equal to 1 joule per second. The power of a circuit depends on the current, which depends on the voltage and the resistance. Coulombs carry the energy like a bucket carries water. More voltage means more energy per coulomb and more coulombs per second. So the voltage does two things. It pushes my electrons around the circuit. It also gives them energy for the coulombs to carry around the circuit. And if you increase your voltage, then you're going to get more energy per second and therefore more power. There are two different types of current: alternating current, which is where my electrons move forwards and backwards around the circuit. The electrons change direction. Mains electricity is 230 volts. The electrons change direction 50 times per second. And to remember, you have to remember that this number here, especially 230 volts, if you were to lick the mains electricity, if you were to lick the plug, then your tooth would hurt you. 230 volts, my tooth hurt you. DC goes in one direction. You find it in batteries. It is also why we have this symbol for batteries and for cells. So this is a cell, this is a battery. Your positive and your negative are shown by the lines, positive and negative shown by the lines. The electrons are pushed away from the negative and the electrons are pulled towards the positive. In plugs, there are three different types of wire that we have to know. Live wires include the brown wire, which is 230 volts. There's 230 volts of potential difference between the live wire and the earth wire and the return wire, a neutral wire. Earth wires are green and white. They have got 0 volts of potential difference between them and the neutral wire, and neutral wires are blue, and they also have 0 volts. Earth wire has got low resistance. So if I've got something that is faulty and it's electronic and there is a fray coming from the wire back into the plug, if I was to touch that metal object and if there was a frayed wire touching it, look at me drawing a finger. Okay, is a hand, and okay, I'm not too sure. Okay, that's my best attempt. All right. If you were to touch that, then the electrical current will be able to move through the frayed wire, through the appliance, into your hand, and then down to the ground, where you would die. This is really, really well drawn, isn't it? So this is my my source of potential difference right here. I'm going to call that an AC source. This can be my live wire coming in, and I'm going to draw my neutral wire coming out. And my neutral wire coming out will go is the return path to the power station. If there's a frayed wire that pops off of that red and starts touching the outside of, let's say that this little purple thing here is a kettle, then the electrons are going to flow through the AC source, through that wire, into your hand and kill you. Now, the earth wire is there to stop that from happening. The earth wire connects to the plug and then to the appliance. Oh, golly gosh. The earth wire connects from the plug. Why aren't you undo? All right, okay. Like I said, new version of Microsoft Whiteboard doesn't work as well as the past one. So the earth wire is in the plug as well, and then that connects down to the earth. So if there is any kind of a fault, rather than going through you, the charge will move through the appliance, through the earth wire, and then down to safety in the earth. I recommend having a look at the video that's on that on the YouTube. Circuit breakers are made of a solenoid wired into a live wire. High current causes the stronger magnetic field to attract a soft iron core to open a circuit. So a circuit breaker is a soft iron core, and it is connected to some kind of a switch. It is put near to a solenoid. If there is a lot of current traveling through that solenoid, then it will increase the magnetic field, symbol B. And if it increases the magnetic field, then the soft iron core that has been put at the end of this switch will be attracted towards the solenoid. That will pull the switch back, which will make the switch not work anymore. Here are some examples of circuits. This circuit has got a DC power pack. You'll be able to see it in your own drawing, but there's a DC power pack, 2 fixed resistors in parallel. There were 2 voltmeters connected in parallel over the resistors, 1 ammeter in each branch, and an ammeter connected in series to the power pack to change the voltage, therefore, and therefore the current, change the settings of the power pack. Absolutely vital that you can say how to change current. How to change the potential difference or the current that's moving through different things in a circuit, different components in a circuit, because you will be asked about how to use circuits to find things like the highest resistance, the lowest resistance, the greatest power consumption, etc., etc. We'll come on to Epic RAVE in just a second. This circuit has got an AC power pack that is 2 dots with a little wiggle in between, and it shows the electrons being moved forwards and backwards. 2 fixed resistors in series. Each resistor has a voltmeter in parallel and 2 ammeters in series with the power pack and resistors. So there's 2 ammeters in series with the power pack and the resistors, because I can draw one line and one loop all the way through those things. In this example, we've got a fixed voltage cell, say at 6 volts, and a variable resistor. Variable resistors can increase or decrease the amount of current flowing around the circuit. To increase the current, reduce the resistance in the variable resistor. So to increase the current, we make the resistance in this go down. If we decrease the resistance, then we increase the current that's going around the circuit, and we can change that as we're doing our experiment to see whether or not those components all react the same to different amounts of current. Each lamp has a voltmeter connected in parallel and an ammeter wired in series. Voltmeter is always in parallel and ammeters are always in series. Now we're going to have a look at magnetism. Like poles attract, unlike poles repel. We know this from key stage 2. Now, if I was to draw a very simple north and south magnet here, then we'll be able to figure out why that is, as long as we remember that Santa Claus is just like the magnetic field. The magnetic field always comes from the north out. So here the magnetic field will be repelling each other before it moves on onto the South Pole. And in the South Pole, magnetic field always acts in towards the South Pole. So Santa Claus goes from the North Pole all over the world every night at Christmas time. Magnetic fields always go from the North Pole to the South Pole as well. Denser magnetic fields mean stronger magnetic fields. So if I was to draw more lines in here, on this magnet on the right hand side, this would be a stronger magnet because it has got denser magnetic fields. Earth's core is magnetic. We know that because compasses are magnetic, and the proof of that is that north points north all the time. There are different types of magnets that we can use for different jobs. Cobalt is used for high temperature magnets, steel for long-term magnets, iron for magnets that we want to have their magnetism lost very quickly, so electromagnets or microphones, and nickel is an inexpensive cover for other more expensive magnets. Induced, excuse me, induced magnets are magnetic in a magnetic field. So if I have a magnetic field and I put something metal in all the way over here, it is not inside that magnetic field up here, so it is not magnetic. If I move it to that second position and I've got my object inside this magnetic field, it is now an induced magnet. Induced means that it is made to be a magnet. You can also wrap an iron core or a nail in a current carrying coil, and then it's magnetized, and then that will become magnetized. This is called a solenoid, a coil of wire with a running through it. You can also do it by what's called running magnets. So if I have a magnet here, north to south, and I put an iron nail on top of that magnet, as if I move the magnet forwards and backwards, or actually I have to move it in the same direction, then it will cause this to become an induced magnet as well. Transformers can increase or decrease induced voltage and induced current. How do they do that? With more coils on the primary or the secondary coil. Excuse me. Transformers can increase or decrease in induced voltage. A solenoid is a coil of wire with a current running through it. That coil of wire will have a current running through it and it will be in a particular direction. So the magnetic field around the wire with current running through it from positive to negative, we call this conventional current, even though it's not actually true in that there's no positive things moving around the circuit. We just call it conventional current because it's what they thought it was back in the day. If you put your right hand with your thumb on the wire and the thumb is going in the direction of the current and you twist your fingers forwards and backwards, the direction your fingers are going are the direction that the field is going. If you want to increase the induced potential difference, you can increase the size of a magnet. Actually, what we're saying here is if I get a coil of wire and I pass a magnet through that coil of wire forwards and backwards, then it will have an induced current and an induced magnetic field. If you want to increase the induced potential difference, increase the size of the magnet so we can get a big magnet. We can have more coils in the solenoid, or we can move it forwards and backwards faster. Left-hand rule, FBI, force BI. B is the magnetic field's flux density, I is the current. Perpendicular fingers show the effect of current carrying wire in a magnet. If you put your finger in the direction that the magnetic field is going, if you then have your right your middle finger perpendicular to your first finger, your thumb will show the direction that the force is moving. I recommend having a look at the lesson that's online for this if you don't know it 100%. But it's the FBI rule, and then make a little gun with your hand to remind you about what the perpendicular things are supposed to look like. Okie dokie, kinetic theory. More kinetic energy means a greater internal energy. This means intermolecular bonds can break because they expand more because of more vibration. So the kinetic theory tells us what's the difference between a solid, liquid, and gas. In a solid, particles vibrate. They can't break bonds, their shape is fixed, and their volume is fixed. However, if we cause it to vibrate more, then it becomes a liquid. Particles vibrate with enough kinetic energy to change shape, but they keep the same volume for the most part. There will be a slight increase in volume, but not enough. In gas, particles vibrate with enough kinetic energy to change shape and volume. So gases take the volume of whatever you put them into. That usually solids have got a greater density than liquids. There is one shocking or one notable difference to that, and that is ice. And that's because when water becomes a solid, it forms a lattice, and that lattice actually is less dense than water, which is why ice floats on water. Volume increases from a solid to a liquid to a gas. There is only a very small increase from a solid to a liquid. However, there is a difference. 1 meter cubed is not equal to 100 centimeters cubed. It is 1 million meters cubed. 100 times 100 times 100 centimeters cubed will equal 100 centimeters by 100 centimeters by 100 centimeters is the same as 1 meter cubed. Always check the units that you're asked for a density calculation. When increasing the internal energy, changes of state happening. So if I have a pot of water and I put some heat into that pot of water, then it will cause a change of state. The internal energy is going to increase, which means the degrees Celsius are going to increase until all of the energy is being used to change the state and not increase the temperature. At boiling melting points, all of the energy is doing just that. It is being used to either break or make bonds to turn something from a solid into a liquid or vice versa. Specific latent heat is the energy needed to change the state of 1 kilogram of a substance, and specific heat capacity, the amount of energy to raise 1 kilogram by 1 degree Celsius. If I have a block of ice that is 1 kilogram, and I put 4,182 joules, I think, not 100% sure on this one, but if I put that amount of I think it is right, that amount of energy into my block of ice, then the temperature will increase by 1 degree Celsius. That is the specific heat capacity. The specific latent heat is the amount of energy needed to change that from being a solid into being a liquid. The specific latent heat is the amount of energy needed to change the state. The specific heat capacity is the amount of energy to raise 1 kilogram by 1 degree Celsius. Gas pressure is caused by collisions of gas particles in the inside of whatever container that you give to them. If you increase the temperature of the gas, then you will increase the kinetic energy. If you increase the kinetic energy, then there will be either more collisions, or those collisions will transfer more energy, therefore increasing gas pressure. Absolute zero is minus 273 degrees Celsius, or 0 Kelvin. This is the temperature at which there is no internal kinetic energy. All particles stop vibrating at the same time, and you are left with an object that is very, very cold. Minus 273 is a theoretical temperature, but it is at the identical scale as degrees Celsius. So if I increase something from 3 degrees Kelvin to 4 degrees Kelvin, that is the same as a 1 degree Celsius increase, because the scale of Kelvin and degrees Celsius is exactly the same. You will be asked a core practical, or at least a practical question in your science exam. Please do not forget that in physics experiments, we're all about measuring values of terms in equations. So if you want to find speed, for example, measure the distance and the time. For experiments or other questions, always try to find an equation that you can use. And don't forget EPIC RAVE. E stands for what equipment do you need to measure the terms? So what equipment do you need to measure the distance? What equipment do you need to measure the time? How would you use that equipment? Well, I need a ruler to measure the distance, and I will put my ruler along the track to measure the distance that the trolley moves, whatever it is. P is procedure. I is independent variable, or how are you measuring the important value? So it's either the independent variable that you are changing in an experiment to see the effect it will have on the dependent variable, or it's the important values or the important value that you are measuring in your experiment, the density of this cup or the specific capacity of that blob of mercury. Do as often as you can, give a control variable. How can you keep all other variables the same? There are some examples down here. Control variables must be limited, so any changes due to the independent variable changing. Circuit diagrams are used for planning experiments. Label one if you draw it. If testing resistance, R equals V divided by I, but you must specify whether it's a series or parallel. You must specify whether it's a series or parallel circuit. You can change potential difference using a rheostat or a variable resistor. It's a symbol with a box with an arrow coming through it. I can change the current that's going through that circuit, because if I change the resistance, for example, I decrease the resistance, I'll increase the current. How do you find the volume? You've got to use an overflow can, which is one of those side arm cans. And if I fill that up completely with water, plop an object in it, the water that comes out will be equal to the volume the water that comes out will be equal in volume to the water that has been displaced by the object, so therefore is equal in volume to the object. But you must use something sensible to measure it. You can't just measure it using your hands, so you must use a graduated cylinder with small scales on the side. Digital thermometers are easier to read and are far more accurate. You must take volume measurements from eye level and not from above. If this is the level of the water, you will always read the bottom of the meniscus. Now, if you were looking at it at eye level, then you will see accurately what the level of the water is. If your eyes are up here and you are looking downwards, then you will get, whoa, that's a weird eye, then you will get an error of parallax. You will think that your water is a lot smaller than what you saw. We can insulate with lids and polystyrene if we're doing a specifically heat capacity or specific latent heat question. So if you test resistance in series, parallel circuits, or resistors and lamps, you must set up two circuits, at least one with a series circuit, one with a parallel circuit, or one with a resistor and one with a lamp, making sure that your voltmeters are in parallel, your ammeters are in series. The procedure would be to record the current and the voltage in each component over a large range of voltages and compare. I'll record current with an ammeter, voltage with a voltmeter, and I will change the voltages by adjusting my power pack. I'm going to find the current using the ammeter, the voltage using the voltmeter, and then using resistance is equal to voltage divided by current to find the answer. Identical intervals when you're increasing the voltage means that you're going to get a far more pleasant graph. So you have to keep things at the same temperature if you're testing resistance, and repeat and find an average. Always don't ever forget the RAVE. R stands for repeat, AVE stands for average. There's no point doing an experiment if you don't repeat it and find the average. How do you measure the density of an irregular object? Use an overflow can like we talked about, a balance to find the mass, and a graduated cylinder to find the volume. Density is equal to mass divided by volume. Always mention the equation that you're going to be using in any epic RAVE. Find the mass of the object using the balance. Drop in the rock into an overflow can. The overflow can will go into a graduated cylinder to find the volume. Density is the important term, so density was mass divided by volume. Some controls that we can think about that we can use in finding the density of an irregular object. You find the mass while it's dry, not when it's come out of the overflow can, because then it'll be wet. The overflow can full to the brim so that you get an accurate change in the volume, and push down floaters. So anything that's floating up on top of your overflow can, so here's my overflow can. If there's something floating a little bit out on top of the water, get a needle or a tip of a pencil, put it underneath the water, and more water will come out. We're here to find the volume and not the amount displaced due to the force of gravity. Measure the specific capacity of water. Use a joule meter, a stopwatch, a balance, an insulated beaker, and a thermometer. Find the mass, take the temperature, start the timer, heat the water, and then stop the timer after a certain amount of time. Because if we're trying to find the specific heat capacity of water, we need to rearrange our equations. So C, which is the specific heat capacity of water, is equal to Q divided by the mass times the change in temperature. How do I find those three things? I find the change in energy using a joule meter, the mass using a balance, the change in temperature using a digital thermometer, because they're easier to read than a normal thermometer. Some controls you might want to do: insulate the beakers so that the heat that is being generated and put into the water isn't wasted to the environment, and use a digital thermometer to read off the numbers because it's easier and more accurate than an analog one. And don't forget as well that we have got to make absolutely sure that we know our symbols, that we know our prefixes, and that we can exchange from something like millijoules into joules. Well, for this one, it will be a divide by 1,000. Always think about millimeters and meters. 1 meter is equal to 1,000 millimeters. How do I turn 1,000 into 1 divided by 1,000? All right then. Thank you very much, everybody, for paying attention. This is paper 2. There's a lot less content that you have to know about in paper 2, but that just means that I'm probably going to be throwing more difficult questions at you. Keep studying. All the best. And the password for this one will be Primark hairbands.